to the number of continuity constraints plus the number of optimization coefficients that we would like to have, plus the number of projectors that we want to develop, minus 1. So we choose the wave vectors for these so they are not quite orthogonal on the set from 0 to RP. You can ask me later if you care why they're not quite. And in order of increasing energy, we calculate each pseudo wave function in turn, satisfying the continuity and overlaps constraints with all the ones we've already calculated. Now, first we find a wave function which satisfied all those continuity constraints using singular value decomposition. And now the singular value decomposition gives us NO, the number of optimization parameters we want, functions that just don't mess with any of our linear constraints. We diagonalize the residual energy operator in this basis, and this gives us a set of eigenfunctions, by the way, that this operator is positive definite. And we now can express our residual residual energy very simply. Our pseudo wave function is going to be the one we already found that matches all our constraints, plus a set of these residual energy functions. Our energy is very simple, and there is a very simple and rigorous way, very robust way to find the set of coefficients which minimizes this. It turns out that these eigenvalues of the residual energy operator span a huge dynamic range, 10 to the 4th to 10 to the 6th. And this is a reason why I had to go to this method, because ordinary methods like conjugate gradient really failed to get the right answer in this problem. So now I'll point out that once we find our pseudo wave function optimized for a given cutoff, we can then go ahead and take our residual energy operator and evaluate it at a wide variety of different cutoff energies. And this gives us, for the particular pseudo wave function we've chosen, this gives us basically a convergence profile. So one thing that is different in this extension to multi-projectors is that in the earlier version of this routine, math was made somewhat simpler by just using one fewer optimization term for the second projector, but keeping that consistent gives reasonably consistent convergent profiles for all our projectors over the whole energy range. So here's what a set of projectors look like, where we are pseudizing not only the valence and shallow core, but we're pseudizing several more shells, in this case for osmium. And these plots come out looking rather pretty, in my opinion, just quite systematic. The 1, 2, 3, 4 are arranged in order of the magnitude of their coefficients in this diagonal non-local operator. And consistently, the one with the largest energy is always in closest, and they step out in a nice, orderly fashion. No, I didn't have an artist make these. They just come out this way, okay, when you've got a good pseudopotential. Now, log derivatives, while we've seen a lot of that, and maybe 10 years ago it was the thing, I don't think anybody has seen log derivatives over an energy range like this before. And here we are comparing the log derivatives for a full potential solution of the radial equation and the pseudopotential solutions for S, P, D, and F. And right down here, we've got this very sharp drop of pi. By the way, I like to take arctangent just because it's much easier to see. I mean, straight log derivative plots have all kinds of divergences. I mean, they're impossible to look at. But anyway, this is down here at about minus 115 or something, where we've got the 3s, and we just step right on up into high positive energies. I plotted these up to 50 Hartrees positive. So that encompasses a lot of conduction bands. Anyhow, going on, I mentioned convergence profiles. This is what convergence profiles look like for a well-designed pseudopotential. for each angular momentum, we get relatively monotonic behavior on this log plot. And somehow this 10 to the minus 5, which is Hartree error per electron, is a magic number. If you just use this outermost point, you typically find you get very good convergence of your condensed matter calculations. Okay, next topic, ghosts. Ghosts are highly localized states which are out of node count order. You don't get ghosts when you have a strictly local potential. It's a characteristic of non-local operators. And there's a sort of quick and easy method to test this without having to do a calculation on solids. You put a hard wall around the around the pseudo-atom. You use eigenfunctions of the local potential as a basis, which can run up to very high energies for accuracy. And ghosts show up when you diagonalize the full Hamiltonian as highly localized wave functions. This is a neodymium potential that a user sent me. He said, I'm getting really funny valence bands. Why? You know, on all your tests, this potential looks okay. And I hadn't developed this ghost testing yet. This is one of the motivations. So here's the answer. Down at 141 Hartree's negative, he's got an F resonance that's pulling 14 electrons out of this compound he was looking at, and he wondered why he had funny looking valence bands and there wasn't any gap, that the Fermi energy was in the middle of some states. Also, you can have ghosts at positive energies, and here's an example from using data from one of the published potentials that shows this sharp drop at around 3 Hartrees that will give you a very flat conduction band stuck in a place where you might prefer not to have a flat conduction band. So this automatic ghost testing, I think, is good to have. Now, I spoke about extreme conditions. The question comes, how do we really test pseudopotentials under extreme conditions? I mean, I don't know of any all-electron codes I can test against that I can push up to tens of Hartrees or more in temperature. And even Abinit, I found, starts to get unstable if I go above 5 Hartrees is about the biggest I've done in any of my testing here. So anyway, I think it's plausible to use what I'll call a bootstrap method, sort of in the same spirit as the ghost testing. I use an atom with a spherical barrier around it, except it's not a hard barrier. I found, just experimentally, shall we say, that if I use a distribution of boundary conditions on that barrier, sort of suggested by Bruin's own sampling, that I do fairly well at fitting temperature dependence with a pseudopotential against an Abinit calculation up to the temperatures where I can keep Abinit stable, as I'll show you in a minute. And the fact is, I can then do an all-electron calculation with exactly that same set of boundary conditions, and I can compare. I'm typically doing pressure versus temperature and volume. I can compare that for all-electron and pseudopotential in this spherical confined atom model that moderately well replicates those things for solids, I believe. So 2 examples here, actinium and tantalum, and I'll work with several different pseudopotentials. Okay, on the upper right here, I've got my comparisons to Abinit. Abinit is, no, that's the electron. Okay, the confined pseudopotential and Abinit are shown here. Okay, Abinit is the purple. Abinit is the one for, this is for the equilibrium FCC structure, and this is for twice the density. So there's a little bit of offset, but the temperature trend is right, and that's what I care about. So I say this is evidence that this is a good enough way to compare pseudo and all-electron to get to these very high temperatures. Okay, now let's go down here and get hotter than hell, shall we say. That's a temperature of 100 Hartrees. So what we see is that for these different pseudopotentials, which have various numbers of electrons kept active, that I want to show actinium first. I guess I skipped it. Well, I'll go back to actinium. Anyway, they peel off from the all-electron curve. You can barely see it here at the very highest temperatures because you basically cooked off all the electrons you had in the pseudopotential. The all-electron potential still has a few more electrons, so, you know, that keeps going. And here I'm just showing the blow up at lower energies. Let me go back for a moment to actinium, where you can see the peel off more clearly. But now let's go on to the next topic, since I'm running out of time. Atomic forces. Most people think you shouldn't overlap non-local projectors. There's nothing in the formalism that says you shouldn't, okay? You're using a plane wave basis. You're describing the electrons the same way in all parts of space. So let's just see what happens when we compare three different pseudopotentials where we go from negligible overlap to substantial overlap. Okay, this is going to be the reference calculation. This is almost doing an all-electron calculation on molybdenum with Abinet. And 5 Bohr is equilibrium for the BCC model. And now we start squeezing the atoms together. I'm superposing all the projectors here for all angular momenta. And, you know, they were barely touching down at 1 Bohr. So this is one case. Here's the next case. We have now just one deep shell active. And when we get around 2 Bohr, we're starting to get substantial overlap. And, you know, that's, you know, by and large, you wouldn't do that. Let's now go to what I call a basic potential. We only have the shallow cores pseudized. And here we've got lots of overlap, ridiculous overlap here over almost the whole range. So how bad do things look for the forces? I suspect some of you may guess they look pretty bad. On the other hand, you might think I wouldn't be showing this unless they look pretty good. So coming back to something about tests on forces, you know, one can devise a pretty good test just by, not by looking necessarily at, you know, fairly obscure asymmetric structures, but by just taking a simple structure, you know, putting an atom where it really doesn't belong and comparing forces among different codes. Now, how you set up standards for this that people will agree on, I'm really not sure. Okay, and just my last example, I said, I've worried about these forces. I've worked on cooking electrons hot, at least, you know, in the pressure versus temperature. What's going to happen to the forces if I get the electrons hot? Well, I had my own guess in my head. I said, well, you know, hot things get sorted, the forces should go down. Not what happens. You get things hotter, woo, look at the forces jump up. Do I have a good explanation for this yet? No. Hopefully, it won't be too long before there is more understanding of these things. But anyway, the whole idea here is that we can use, in fact, these pseudopotentials with deeper cores activated. I should mention in passing that every potential I've showed you, and many I haven't, I have run conventional benchmark testing at ambient conditions, and all these ones with the deep cores do just as well as the standard ones with at most shallow cores. Higher cutoffs, yes, but not absurd cutoffs. In fact, that molybdenum, I can go into the same depth of quantization with a cutoff of 350, where I do have more overlap, so I just didn't want to use that for my force example. Now, I want to point out a few limitations. Generalized norm conservation is only valid with a strictly local potential. And I found that scalar relativity and actually fully relativistic calculations are available for all of this as well. Effectively introduces the first derivative operator into your radial Schrodinger equation. This creates errors typically of order 10 to the minus 4. But we treat this in an ad hoc fashion in a couple of places where we need to get rid of it. And however, one thing that this tells me is to stay away from hybrids and meta-GGAs because I believe they can only be treated properly within an OEP, optimized effective potential approximation, and that's probably not worth doing. Probably pays to just treat more electrons by whatever, hybrid or meta, by putting another shell and just using a density functional pseudopotential with one more active shell. And I will point out that the release that incorporates everything I've told you is now available on the web, and this is an open source project, so I welcome contributions. Thanks for your attention.